It's a great pleasure and especially a great honor to have the only surviving solver of one of Hilbert's famous problems, Yuri Matiyasevich, who famously solved the most interesting problem of Hilbert, the 10th problem about the undecidability. And Yuri now moved on to, I think it was Hilbert's 6th problem, the Riemann hypothesis. Go ahead. As usual, if you have questions, please unmute yourself and ask it, but otherwise mute yourself. Thank you.
I am very grateful to the organizers for giving this opportunity for me to speak about my recent research. There will be no new theorems, and it's not so easy to publish a paper without new theorems with only conjectures and results of experiments. So I'm really happy to be at this seminar. My talk will consist of 2 parts. In the first part, I will remind some known facts from number theory. I am sure that many of you are familiar with these facts, but I wish my talk to be self-contained. And after that, I'll present my numerical experiments and what I was able to discover. So part 1, some facts from number theory. And I start from very, very old number theory, from the famous sieve of Eratosthenes. How it works, we start with natural numbers 2, 3, and so on. We declare the first number to be a prime number, and then select every second number, and allow other numbers to fall down. We declare the first number to be prime, select every third number, and allow other numbers to fall down. And then we repeat this process, 5 is prime, every 5th prime, 7 prime, every 7th number, and so on. And in this way, we will find all prime numbers. But nowadays, a more important tool for study primes is connected with so-called Riemann's Zeta function. This is a function of complex argument S, which can be defined by this Dirichlet series. The series itself converges only in the half plane where the real part of S is greater than 1. But it defines a function which can be analytically extended to the entire complex plane, except for the point S equal to 1, where it has its only simple pole, because at S equal to 1, we have divergent harmonic series. In fact, the same function was already studied by Euler, but only for real values of S. Euler made several contributions to the study of this function, and one of them is known as Euler identity. Actually, Euler gave another definition of the same function. The original definition is in the form of a sum, and Euler's definition is in the form of a product. What is remarkable with this new definition? Here we have, so to say, homogeneous expression where we just run over all natural numbers, but here we have product only over prime numbers. At first, this looks rather surprising. How to prove it? How we can pass from all numbers to prime numbers? You know that this could be done by the sieve of Eratosthenes. And so I will present the proof given by him. We start with the zeta function, such an infinite sum. And as you remember, the first step, we need to eliminate all even numbers. What it means to eliminate when we deal with the sum? We need to subtract all these even powers. And what is the sum of all these numbers? It's easy to see that it is just the product of zeta of S multiplied by this factor. So we add these 2 lines and we get that this product, zeta of S to this factor, gives such Dirichlet series over odd numbers. And now we repeat the trick. We have here the series with odd numbers. We need to eliminate numbers divisible by 3. We take this product, multiply by this power of 3, add these two numbers, and get that the product zeta of s, this factor, gives us a Dirichlet series where there are numbers divisible either by 2 or by 3. And we continue it up to infinity. And what would be the result? On the left-hand side, we will get the product of zeta of s multiplied by all such factors. And on the right-hand side, only 1 to the power minus s would survive. All others will be cancelled. But this is just number 1. And we get what we needed. We got the Euler identity. This is a very simple fact, but it explains the power of the zeta function. It explains why it is so important tool for studying prime numbers. And already Euler used it to demonstrate the possibilities of this identity. Namely, he gave a new proof of the very well-known theorem by Euclid about the infinitude of prime numbers. Euler's proof is as elegant as Euclid's, I would say. It's just one phrase. If the number of primes would be finite, then the divergent harmonic series would have finite value. In fact, if we substitute here s equal to 1, on the left-hand side we have infinity, so this product cannot be finite. What we know about the zeros of the zeta function? Already Euler indicated that even negative integers are zeros of the zeta function. And these numbers are called trivial zeros of the zeta function. Riemann began to study this function for complex argument, and he proved that all other zeros, which are called non-trivial, are non-real, and they are located inside so-called critical strip, where the real part of S is between 0 and 1. And more important, he made a guess, known as the Riemann hypothesis, that in fact, all the non-trivial zeros of the zeta function are located exactly in the middle of the critical line, or in the critical strip, on so-called critical line, where the real part of S is equal to 1/2. The Riemann hypothesis has a lot of applications in number theory. Thousands of theorems are nowadays proved only under the assumption of the Riemann hypothesis. So let us summarize what we know about the zeta function. This is the complex plane. At point 1, we have the only pole. At points -2, -4, -6, and so on, we have the trivial zeros. The green half plane is the half plane where the Dirichlet series converges. In pink, we have the critical strip. In the middle, the critical line. And here there are 4 non-trivial zeros of the zeta function. They are distributed rather unevenly. But what is important for us is the following. Thanks to this relation, if we have a non-trivial zeta 0, then its complex conjugate is also a 0. Non-trivial zeros always comes in pairs. However, consider also another function, so-called alternating zeta function, eta function, which is defined by a similar Dirichlet series, but now the coefficients alternate between +1 and -1. These two functions are closely related. It is easy to verify that eta function is just a multiple of the zeta function. But eta function has 2 advantages over the zeta function. First of all, this series converges in the larger half plane where the real part of S is greater than 0. And this allows, for example, to calculate the value of S inside the critical strip just by calculating the value of eta function and then by dividing by this factor. And second advantage is that this factor vanishes when S is equal to 1. Thus, it cancels the pole of zeta function, and eta function is an entire function, and it is usually more convenient to work with an entire function. Now let us calculate a bit. Let us calculate the value of the eta function at S equal to 1. We will know that the value is equal to natural logarithm of 2, which has this value. But computer cannot make an infinite summation. We need to stop some point, so we can calculate only finite sum. And if we sum 1000 terms, we will get such a value which has only 2 common decimal digits. And it is easy to understand why it's so. The sums oscillate around the limiting value, and the size of oscillation is 1 over n. So we got the error about 1000 according to this term. But we can make the following trick. We can sum n-1 terms and take the nth term with the factor 1/2. And this dramatically increases the accuracy. If we sum 1000 terms here, we will get this value, which has 6 common digits with the true value logarithm of 2. But in this direction, one can go further. And for example, Peter Berwein suggested another approximation to the eta function. He defined finite approximation with some coefficient alpha. The alpha was defined in the following way. He took the coefficients from the eta function and multiplied by such difference. He gave explicit value for these betas, which is not of no importance for us. And if we take only 30 terms of this approximation, we will get more than a dozen of correct decimal digits of logarithm of 2. Why is it possible? Let us look at this factor. That's the plot of this factor. And we see that it starts as almost 1s, and then gradually decreases to 0. And thanks to this gradual truncation, we get such great accuracy. And it is a kind of a skill to invent a proper truncation. Now I can pass to telling about my own experiments. My original idea was very simple. We have an infinite series, and I wanted also to define a finite approximation to the zeta function. It will be denoted omega L sub s. The question was how to define these coefficients. Berwein gave explicit expressions for his coefficients. My idea was different. I just demanded that we need to have good properties of this sum. Let us define numbers delta sub n by the following conditions. First, we demand that this finite sum should have n-1 common zeros with this infinite sum, with the zeta function. Of course, we can just take all the deltas equal to 0, but that's of no interest for us. To avoid such degeneration, we introduce additional condition, a kind of normalization. We will demand that the first coefficient should be equal to 1. So here is just a formal definition of our approximations. We will always take n equal to m plus 1, and we want to find approximation of this form. And these deltas are defined by conditions that the finite sum vanishes at m initial zeros of the zeta function and at their conjugate values. Here, rho 1, rho m are the initial zeros of the zeta function and the half plane. And we can assume that they are ordered according to the size of their imaginary parts. How could we find these deltas? Quite easily. These deltas come here in a linear form way. So actually this condition is a linear system with 2m equations and 2m unknowns, the deltas. So we can just solve this system. And I remind you that we decided that the first coefficient would be equal to 1. Now let us compare the zeta function along the critical line and our approximation when the capital N is equal to 17. Here are the plots of the real parts, and here are the plots of the imaginary parts. Red for the zeta function, and in blue for our finite approximation. And we see that initially there is a great discrepancy, but later the blue color completely covers red color, so this is a good agreement between our finite sum and the zeta function. And how we got this good approximation? If we look at the coefficients, we will see that they behave very familiar to the coefficients in Barwein's case. Initially, coefficients are approximately 1, and after that, they gradually decrease. This coefficient was 1 by definition, but why other coefficients are 1s? We did not demand them to be close to 1, we just demanded that the finite sum should vanish at the zeros. And remember that we work on the critical line that is outside of the half plane where the series converges. So we can say that non-trivial zeta zeros knows a lot. In particular, they know that at least initial coefficients of the Dirichlet series for the zeta function are approximately equal to 1. And also, this is very remarkable that here we got a smooth truncation which produced a good approximation of the finite sum by a good approximation of the infinite sum by finite sum. Barwijn invented his truncation by looking at one integral representation of the zeta function. And here it was the pure computations. We first computed the zeta zeros and then solved a linear system. So I can say that non-trivial zeta zeros know that a smooth truncation can give a good approximation to the zeta function, at least on the critical line, outside of the half plane of convergence of the Dirichlet series. We can examine these plots more carefully. Of course, this function vanishes at the 8 zeros used for construction this finite approximation. But we can see that even after these zeros, we have here quite good coincidence of the two plots. And in particular, this finite sum vanishes near the zeros of the zeta function. We used only 8 initial zeros, and omega 17 vanishes near the 9th zeta zero. The discrepancy is less than 1,000. It also vanishes near the 10th zero. Here the error is a bit greater. But this was a rather small number, 17. If we take n equal 101, we have much better approximations. This finite sum vanishes very close to the 51st zeta zero. The discrepancy is less than in 15th digits. Next zero is approximated a bit worse with 14 digits and so on. So we can say that zeta zeros knows a lot, and in particular, they know approximate values of several next non-trivial zeros. This is a very interesting phenomenon. I imagine that we would approximate zeta function not by Dirichlet series, but by a polynomial. There is no problem to construct an interpolated polynomial, but it wouldn't give us no other zeros except those used for its construction. But here, using a fixed number initial zeros, we can find approximate values of next zeros. And even more is interesting. Here I will show you how this finite sum behaves near the trivial zeros, -2, -4, and so on. And we see that this finite sum vanishes very close to the trivial zeros. So non-trivial zeta zeros somehow know about the existence of trivial zeros. We gave no hints to the trivial zeros. We used only non-trivial zeros for calculating the coefficients. Nevertheless, we can get approximate values of the trivial zeros as well. So non-trivial zeta zeros know also about the initial trivial zeros. Now I will show you the plot of coefficients for n equal 101. And it looks rather different from what we have seen for n equal to 17. When I saw this picture for the first time, I believed that there is a mistake in my program. No, it's quite correct. And I can say that for large n, the picture is like this. The coefficients alternate between initial coefficients, between +1s and -1s. So they behave like coefficients of the alternating eta function. And again, we can informally say that non-trivial zeta zeros know about the existence of the alternating zeta function. How it is possible? Let us examine our definition of the omegas. We define them in the following way. We said it should be of this form, and the coefficient deltas were defined by condition that these sums should vanish at m pairs of the zeros of the zeta function. Zeta function vanishes here, and omegas also should vanish at the same numbers. But eta function is a multiple of the zeta function. So it vanishes also at the same numbers. So our definition of omegas does not distinguish between the zeta function and the alternating zeta function. And so it's interesting why for small n equal to 17, omega mimics the zeta function, but for large n, it always mimics eta function. My only guess is that it prefers to deal with the entire function. But then there is another question. We could kill the pole of zeta function by many other factors. Why the same factor, which was invented by Euler in order to extend the area of definition of the zeta function? As I said, eta function vanishes as soon as zeta function vanishes. But also eta function has its own zeros, which I call extra zeros. Zeros which are due to this factor. They have the following form: 1 plus this imaginary part. And our finite approximation also vanishes near these zeros, near the zeros of this factor. So again, we can say that non-trivial zeros of the zeta function somehow know about the initial zeros of the eta function, zeros which are due to this extra factor. Now I will show coefficients for n equal to 3101. It's very typical picture, but what can we see here? We see that coefficients alternate between +1 and -1, and it looks like quite horizontal lines. Not much could be seen on such a picture. So we will do the following. We will take our coefficient. It is close to 1 when n is odd and close to -1 and n is even. We subtract 1. This difference will be close to 0 for odd n and close to -2 for even n. We will take the absolute value, decimal logarithm, and now I will show you the plot of these quantities. It looks like this. My question, have you ever seen such a picture? No? Let us analyze this picture.
Ratospensive.
Sorry?
Ratospensive.
Yes, great. So let us examine this picture. We see that the points have the tendency to lie on horizontal lines, which I will call levels. On the top level, we have points which correspond to even values of n. Then this quantity is -2, and so this is just decimal logarithm of 2. On the next level, we have numbers which are divisible by 3, but not by 2. On the next level, we have numbers which are divisible by 5, but not divisible neither by 2 nor by 3. On the next level, we have numbers which are divisible by 7, but not divisible neither by 2, nor by 3, nor by 5, and so on. Here, divisibility by 11, but not divisibility by previous primes. Here, divisibility by 13, but not previous primes, and so on. And so what are the numbers here? They're just prime numbers. And as it was already mentioned by someone, we can say that the plot of these quantities is just a graphical representation of the sieve of ratiocinus. So somehow non-trivial zeta zeros know about the sieve. Ratiocinus was a human being. He invented a process, and here it was just a straightforward stupid calculation, first of zeros and then of these quantities deltas. Let us examine more carefully this level, where we have points corresponding to n divisible by 3. Of course, they are not equal, and we repeat our trick. We will consider every third coefficient. We will subtract now not 1, but the first coefficient. We can take absolute value and decimal logarithm. And now the picture looks like this. It again looks similar to the sieve of eratosthenes, but there are differences. On the top level, we again have even numbers. But on the next level, we have numbers which are odd and divisible by 5, but they could be divisible by 3, 15, 45, and so on. On the next level, we have numbers which are divisible by 7, not divisible by 2, not divisible by 5, but they could be divisible by 3, 21, 63. At last here, we have numbers which are divisible by 3, but not by 2, not by 5, not by 7. And then it continues in the standard way. Here, divisibility by 11, but not divisibility by previous numbers, prior numbers, divisibility by 13, 17, and so on. And again, in the rest, we have prime numbers. So we can say that we have a kind of the sieve of eratosthenes, but now the order of primes is different. The order is 2, 5, 7, 3, 11, 13. And at first it looks surprising. Why 3 is between 7 and 11? But it's not difficult to understand what is the reason. Here we used every third coefficient. Divisibility of m by 3 implies that this index is divisible by 9. And 9 is exactly between 7 and 11. And I expect that similar picture would repeat if we try to examine more closely these numbers. They also will split into further sublevels. And my guess is as follows. If n range over an arithmetical progression with step d, which has such factorization, then corresponding sublevel splits according to the divisibility of m by prime numbers q1, q2, and so on, where these are the prime numbers ordered in such a way that such an equality holds. In our case, m is equal to 3, the step of progression. K2 is 0, K3 is 1, all other cases are zeros. So Q1 is 2, Q2 is 5, Q3 is 7, Q4 is 3, Q5 is 11, and so on, according to these inequalities. But non-trivial zeta zeros produce also another kind of sieve, which I call dual sieve. It can be seen when we plot such quantities. Let us sum our deltas up to some limit. If m is even, then there will be equal number of deltas approximately equal to plus and minus 1. So this will be approximately 0. But if m is odd, then there will be one extra 1 over minus 1, and the sum will be close to 1. And here is the plot of these quantities. The structure is as follows. On the top, we have all odd numbers. On the next level, we have numbers divisible by 2, but not divisible by 3. On the next level, we have numbers which are divisible by 2, by 3, but not by 4. On the next level, we have numbers which are divisible by 2, by 3, and by 4. Here we have numbers which are divisible by 2, by 3, by 4, and by 5. If we continue and reach the number 420, it is divisible by 2, by 3, by 4, by 5, by 6, and by 7, and corresponding point drops a bit lower. If we go further and reach 840, we will get a point again lower. So again, we have relationship between zeta zeros and prime numbers, but quite different from the picture which we have with the sieve of Eratosthenes. And I call this plot the sieve dual to the sieve of Eratosthenes, and it is dual in a quite technical sense. Okay, formally it can be described as follows. Let us introduce the notion of inheritable divisor. K is an inheritable divisor of M if it is a divisor of M, and all previous numbers also divide M. And we can consider maximal inheritable divisor. It is a inheritable divisor of M, but M is not divisible by K plus 1. And this dual sieve can be described as follows, that the numbers are located on different levels according to their maximal inheritable divisors, while in the sieve of Eratosthenes they are located according to their minimal prime divisor. All this is rather interesting, surprising, but the question is how it could be proved. Several years passed since this was discovered and nobody was able to prove it. And typically, a relationship between zeta function and primes is deduced from Euler product. But here it is not clear how we could use Euler product to explain these sieves, because we use not coefficients of the series, but we use the zeros of the series. And so the Euler product is somewhere far from our picture. And in this respect, it was interesting to consider another function. Oh, sorry, I haven't explained why it is dual sieve in technical terms. So this is the sieve of Eratosthenes. We have all natural numbers. We consider every second, every third, every fourth, every fifth, every sixth numbers. We remove the red tape, and numbers are distributed now according to their least prime factors, as in sieve of Eratosthenes. And this corresponds to the plot of these quantities. But now we can do the following. Let us fill the gaps between these blue parts by green color. And now we remove the blue parts, remove the red strip, and numbers now are distributed according to their maximal inheritable divisor. Here only odd numbers, here numbers divisible by 2, not by 3, here divisible by 2 and 3, but not by 4, and so on. So in this sense, this sieve is indeed dual to the sieve of Eratosthenes. And this corresponds to consideration of plots of these quantities. The following function was well studied in number theory. It is interesting by the following reason. It is defined by a Dirichlet series with coefficients which are defined according to the divisibility of n by modulo 5. This function has many properties similar to properties of the zeta function, but this function has no Euler product. It was interesting to see if this function would have something similar to sieve of Eratosthenes. And in fact, there is a kind of sieve, but it is a bit different from what we have seen before. And here is the divisibility by 5 plays a special role. On the first level, we have numbers divisible by 2, but not divisible by 5. Here numbers divisible by 3, but not divisible neither by 2 nor by 5. Here we have numbers divisible by 5, but not divisible by 25. numbers which are divisible by 25 are situated lower unless they are divisible by 5 cube. Numbers divisible by cube of 5 are still lower. Otherwise, here we have numbers divisible by 7, by 11, and so on. So the absence of Euler product doesn't prevent us from having a kind of a sieve. And all these pictures I showed you, only initial part of the plots. And here is the total plot of these quantities. We see these levels. Before I showed only the first up to 300, this part. And we see these levels of numbers divisible by 2, by 3, by 5, and so on, stop as soon as they touch this strange curve. Why it happened, I cannot explain. And I was curious, what is the form of this curve? So if you ever have seen such curves and have suspicion that it would be the same curve, please let me know. And empirically, I made the following conclusion. We can scale the plots of these quantities. We will divide them by capital N, and we'll normalize this x also. And then my guess was the limit, and there will be a limit defined by this strange looking function. And I was very much surprised when once I saw the very same function in the study of zeta function, but in a different context. So maybe this is in fact the genuine form of this limiting curve. So this is just to show you that in fact the world is not as easy as we can expect. I was calculating the points for many values of capital N, and once I was encountered with such a picture. It's a kind of Gibbs phenomenon. At first, I again suspected that there is a problem in a mistake in my program, but in fact, this is true. So before going to very, very small values, somehow these coefficients became a bit more than 1 in absolute value. Even more striking picture is for n equal to 233. They are plus minus ones, but then they suddenly became very large in value, and they change upper and lower part of the plots, and then again they became very small. And so it's not clear why such sporadic pictures occurs every now and then. No idea whether it's what properties of this capital N cause this strange sporadic behavior.
Is this 233 specific? Are there other numbers like it with a similar property?
There are many of them. Every now and then, some has very peculiar. Usually they are typical, but yes, it happens for many other values.
Amazing.
So maybe it's another sequence of the OIS. You have a specific ones, the first 20 terms that you can put as the OIS of capital N that have this behavior. That'd be interesting.
Okay. So I told you about some of my discoveries. Actually, there are more things. For example, for the zeta function, we have a very important property, so-called functional equation. And so far, we did not touch it, but another way to define these deltas was to demand that our finite approximation should satisfy this functional equation. Then we get different deltas which have also interesting properties. And if you are interested in this area, you can go to my page in the internet, There are many of my papers and devoted to the zeta function. And in particular, these three texts are about what you heard about today. Thank you very much for your attention.
Thanks so much. Please unmute yourself and thank Yuri for a fascinating talk. We have time for questions. Any questions from the audience?
Actually, I do have. Yeah, I have. Hi, Doron. Thank you very much for a really wonderful talk. But I have a comment to make. It struck me that your formula for the red curve that approximates that dotted curve that truncates your horizontal line, that looked like a sum of three entropy terms.
Yes, the entropy. Yes.
If you could go back to your slides there. Yeah, when you look at your formula at the bottom, right? So this looks like three entropy terms. I mean, everything that depends on n, and then there's an offset at the end. So that's very curious to me. I'm just making that.
Okay, please send me a reference to. Could you send me a reference to this?
Yeah. I mean, I can definitely do that. There's a well-known expression that shows up in many fields of science, of statistical mechanics, information science, etc. So this is quite curious. No? So why you have these terms? Yeah, I will send you something. Sure, absolutely.
Thank you.
Can you say anything about the generalized Riemann functions? Like the other, you mentioned another Dirichlet series. But
yes, I haven't made much calculations, but yes, it's similar.
It's fascinating, and everything you talked about is still officially conjecture, right? You have any proofs yet?
No proofs.
Wow, it makes it all the more fascinating.
Also, there are many things to calculate. There are many conjectures what to calculate, what could be expected.
Yeah, it's fascinating.
Yeah, that was a wonderful talk.
Any more questions? Thanks so much. We let Yuri go to sleep. It's almost 2 a.m. in St. Petersburg. Thanks so much for coming, everybody. And,
thanks a lot.
And Happy New Year. Thanks so much, Yuri. And
thank you very much.
Thank you. Bye-bye.
Bye.
Thank you.